Hello, everybody. My name is Wei. Today I will present a paper titled as Embracing Collisions to Increase Fidelity of Sensing Systems with the cut of the shelf text. This is a joint work with my colleague Jiaqi Xu and my advisor Kanes Srinivasan from Department of Computer Science at Ohio State University. So as we all know, RFID-based sensing systems have been widely exploited in Internet of Things era. So RFID stands for radio frequency identification. They have been used extensively in building low-cost sensing and identification systems, such as supply chains, electronic passports, payment systems, smart homes, unmanned supermarket, and so on. Collision caused by simultaneous tag response is one of the key issues in RFID systems. As we mentioned before, the tags will randomly choose a time slot to respond to RN16 package without coordination, thus making the collision an inevitable issue in RFID systems. When collision happens, the collided data which cannot be decoded are viewed as useless and discarded. So the right figure shows the whole process for a reader to interrogate the tag. So how collision affects sensing systems? We discuss how collision affects sensing systems. When collision happens, only one tag whose RNC can be decoded can send the EPC message. The other tags need to select another time slot to transmit. Typically, different RFID tags have different channel gains, or even distribution in channel gains can lead to some tags being read much more frequently than the others. The reader can usually decode the RN16 with the strongest signal. Here we define time resolution of one tag as the number of channel states that can be successfully measured between itself and the reader within 1 second. So this figure illustrates the time resolution of 8 tags. Tag 3 can achieve a time resolution up to 11.18 channels per second, and tag 1 has the worst time, which means it can only be read less than 3 times every second. However, the accuracy of sensing systems depend on how frequently you can get the channel information. Hence, collision can be a severe problem in sensing systems. So previous MAC layer solutions usually design new access mechanism for RFID systems. However, such solutions become expensive to achieve since they rely heavily on system management infrastructures and computational assumptions. So there's a growing interest in physical layer solutions as it can not rely on this. Some anti-collision approaches have been proposed in recent years. Such approaches enabling parallel decoding using the collided data. However, such cluster-based approaches have 2 drawbacks. Firstly, they only support 3 to 5 tags, as shown in the figure. When the number of tags increases, it is very hard to separate all clusters. However, in most sensing systems, they require a large distribution of the tags. Also, anti-collision methods are designed for communication systems, not for sensing systems. They require to change the procedure of communication when the tags need to transmit EPC packets in parallel, which means that such systems cannot work for commercial tags. Most RFID-based sensing systems capture the changes of the environment by measuring the channel fluctuations of tags. The main purpose of sensing systems is to measure the channel rather than decoding. Hence, our core idea is to acquire the channels of all the collided tags and match the channels to the corresponding tag without decoding. In this way, we can enable parallel sensing for the commercial RFID systems without any modifications on the text side. As we can see in previous work, if there are n tags, that means we need to classify 2 to the power of n combinations of different states. But in our work, since one tag has one channel state, if there are n tags, there are only n channels. So we show the framework of our proposed system COFFEE represents a collision-free RFID-based sensing scheme. COFFEE collects the raw samples from the receiving antenna and recovers the missing channel information from the collision data. In this way, we can get the channel information of each tag more frequently and thus increase the fidelity of the sensing systems. Our systems work as an extension to the current standard. So our system can assist all the RFID-based sensing systems that utilize the fluctuation of channel information to do the sensing. So we will go through the design of COFFEE step by step in the following pages. But first, we want to describe the key observations which will support our design idea, and then introduce the detailed design of channel extraction and tag identification. So the first key observation is various response delay, which is defined as the time interval between the reader's query command and the text RN16. The length of response delay is determined by many factors, such as the location, temperature, location, manufacturer of the tag, and so on. Typically, such variation of response delay can be captured by the reader because the reader usually has a much higher sampling rate compared to RFID tags. As we can see from the bottom figure, 2 tag has very different response delay. So the second key observation is the stable bit duration. The bit duration is defined as the time for one tag to send 1 bit. For one tag, the bit duration is only determined by its clock, and the clock is only related to the environment factor, such as temperature and moisture, which does not change across time or space. Bit duration of different tags can be various. For one single tag, the bit duration only fluctuates within several bits. The figure shows that the average fluctuation of the bit duration of one tag is around 0.4 millisecond, which is 4 samples when the sampling rate is 10 megahertz. The third observation is a continuous channel variation. So the channel of one tag is defined as the channel between the tag and the reader in time domain. Typically, the channel of one tag usually changes within some range during coherence time. So these 2 figures show the change of one tag's channel in time domain. Even when there exists human activity between the tag and the reader, the adjacent channel will still change within some range. Since the channel of one tag can be missing due to collision or missing a transmission failure, we also need to take such significance into consideration. Furthermore, the channel between text and the reader can change due to human motion in RFID-based monitoring system. We want to explore how rapidly the channel changes under such scenarios. We use a different metric delta to measure the change between 2 channels, H1, H2, as represented in the equation here. H1, H2 are the complex value of 2 channels. So this figure illustrates the change of channels versus the different time intervals. IR represents the inventory run. Delta is small, even in dynamic environment, which indicates the continuous change of the channel. So after we illustrate the 3 key observations, we need to extract channel based on these observations. So we describe how we extract channel of multiple tags from the collected data sequentially. So our core idea is to separate one data stream of collected tags based on the order of arriving time and cancel the transmit data of this tag after channel estimation. Then we will repeat this procedure until the collected data is subtracted. So based on our first observation, the signals of different tags usually arrive with different response delay. The figure illustrates the procedure when multiple tags join in this figure. So before the data stream of the first tag arrives at the reader only receives the 0 bits. After one tag joins, the signal steps to non-zero bits. When the following tag joins, the level of the non-zero bits changes. Hence, we can obtain the clean channel of the first tag since there must exist a time when only the first tag is transmitting. So after we getting the channel of this tag, we need to identify the tag. Traditionally, the tag ID can only be decoded from EPC message. Previously, simultaneous sensing work like fireworks, they also require tags to transmit the EPC package together and decode the tag ID from the package, which changes the current C122 standard. However, our work goal is equivalent to acquiring the corresponding tag ID without decoding. That's the reason why our work can support commercial tags. Due to channel fading and multipath effect, the channels between different tags and the reader are different. Hence, we can use the channel information as fingerprints of the RFID tags to identify them. Although channels can be viewed as continuous change within a short duration due to the dynamics of wireless link, channels can vary a lot beyond the coherence time, especially when for sensing systems where the objects keep moving all the time. To deal with this issue, we propose a weighted streaming nearest label classification algorithm, as we show here. Different channel will have different weights based on the timeline. In this way, we can identify the tags based on the extracted channel and the history channel profiles, even when channel change over time. As we can see from the left figure, we can classify the collision from 10 tags, and they show clearly 10 clusters in IQ domain. Since the preambles of RN16 are predefined and the channel of one tag is known at this time, the data that transmitted of one tag can be predicted and extracted from the residual data. Bit duration for one single tag can fluctuate in several samples based on our previous observation. One bit duration can result in some spikes in the residual data after cancellation. To resolve this problem, we apply a median filter to remove the random peak after canceling the collision data of one tag. The figure plots the procedure of canceling transmitted signal of one tag one by one. By repeating the previous procedure, we are able to recover the channel of all the collected tags and identify them, as we can see from these figures. So due to the dynamics of wireless channel and the noise, errors are inevitable when extracting channels and matching the channels with the corresponding tags. The errors can lead to either missing or unwanted channel information. Then we discuss the reasons and present the possible methods to avoid the problems. Firstly, wrong channel estimation can be caused by the procedure of collision separation. If the signal of different tags arrive in same sample, it is hard for copy to separate the collected tag data. To decrease the occurrence of missing collision separation, we can either increase the sampling rate or increase the diversity of tags channel. Secondly, wrong tag identification can be caused by similar channel. If different tags have similar channel in a constellation domain, it is very hard for coffee to distinguish the channels. We can increase the distance between tags or use tags from different manufacturers to increase the diversity of the channel. Also, we should periodically calibrate the channel profile using the channel extracted from ETC packet. So this graph shows the operation workflow for error detection. Basically, we measure the distance between the obtained channel and the adjacent channel in channel profile to decide that if its extracted channel is kept or discarded until the residual power is smaller than the noise flow. So in detail, before stored into channel profiles, the temporary channel information needs to pass the error detection block in case we need to add unwanted channels into channel profiles. The error detection is twofold. First step is to detect whether we successfully separate or collided the data by examining the average power of residual data after canceling all the tags if the average amplitude of residual signal is much larger than noise flow. It indicates failure of extracting collided data. Secondly, we compare the difference between the channel and the adjacent channels residual restored in the corresponding channel profiles. When the difference is beyond the threshold, it indicates that the channel can be wrong. When error detected, we discard the wrong information. Otherwise, we restore the extracted channel in channel profiles. So in our evaluation part, we mainly evaluate coffee in practice. We build a prototype and run experiments in real world environment. We build a prototype using commercial VHF tags and software-defined radio like VSRP N210. To achieve sufficient wireless channel diversity, tags need to be located separately. Previous passive tags are attached on the wall and separated by 15 to 30 centimeters apart, which is larger than half valence at the carrier frequency of 910 megahertz. The distance between the tags and the reader is between 1.5 to 2.5 meters, which allows people to move around in between. So first, we run some micro benchmark experiments to validate the components of coffee separately. In this section, we investigate how efficient coffee can separate and extract channel from collision when the number of tags increase. So the figure illustrates the probability density function of the number of channels extracted from collision. The results indicate that our system can extract more channel when the number of collided tags increase. Previous work can only support 3 tags simultaneously transmitting. In our system, even when there are 8 tags, we can still obtain sufficient channels from collisions. Since our scheme can allow more tags to transmit simultaneously, the tags can transmit more frequently, which means that our system can get much more channels. Then in this part, we do experiments to evaluate the channel estimation accuracy for device-free sensing and with device sensing. For device-free sensing, meaning the tag is not attached to the sensing object. The results in these 2 figures show that error remains relatively low even when 8 tags collide. So then for with device sensing, meaning the tag is attached to the sensing object and the sensing object may move around within reader's communication range. As we can see, when the tags move faster, the errors increase and our system will support less concurrent sensing. So in this part, we mainly evaluate the accuracy of our tag identification algorithm. The results show that our identification algorithm can still achieve a high prediction accuracy up to 0.99. And the worst case is 0.93, even when human moves around. So to evaluate the benefits when deploying multiple RFID tags, we measure the average time resolution gain of coffee over C122 with system level tests. We run experiments in a total of 150 randomly chosen topologies with 4 to 16 tags being employed. We can see the median gain with 4, 8, and 16 RFID tags is around 2.34 times, 2.9 times, and 3.42 times on average. So in order to understand the benefits of coffee in RFID-based sensing systems, we implement an activity recognition system based on the approach in reference 39 and apply our system on the top of it. We conduct 6 kinds of human activities. The table illustrates the confusion matrix with without applying our system coffee. From the results, we can see that our system can significantly improve the performance of RFID-based sensing systems. So in a conclusion, this paper, we propose coffee, first system that can harness the collision to improve the fidelity for sensing systems using COTS tags. Coffee can be treated as an extension to C122 standard, which can be applied for all the RFID-based sensing systems without modification on tag side. These are the reference of this presentation. With all that being said, I'm happy to take any questions. Thanks.